Hi, welcome students to the online class for the electron devices and circuits. This is supposed to be your third semester of electrical and electronic engineering. So, in this subject, we are going to deeply study about the various semiconductor devices, how the structure of the semiconductor devices appear, and the various operations and the characteristics of this. So, as far as the first unit is concerned, we will be concentrating on the PN junction devices. The PN junction devices usually include the diodes. So we'll study more about the diodes, and for the diodes we'll start with the structure of the diode, how it is manufactured, and then how the diodes operate, and then the characteristics of the diodes, and followed by the internal function of the diodes. We'll explain, have a derivation on the diffusion and the transition capacitance. And rectifiers, the next topic, is supposed to be then one of the application of the diodes. So rectifiers, it converts your AC to a DC signal. So how we will see how this diodes are going to help the AC signal to convert to a DC, and followed by we will have display devices like light emitting diodes, which is called as LED, and the laser diodes. The next important family of the diodes is the Zener diodes. So Zener diodes, we will see how it is also structure of this, and we will see this operation, and followed by we will see an application related to this as a regulator. So regulator, which regulates either the voltage or current. We'll see how this Zener diode is going to help the voltage or the current, how to be get it regulated. So coming into this unit, we'll see about the PN junction diodes. So PN junction diodes are very common in every applications. You take a domestic application or you take an industrial application, these diodes are very important, and they have been using for years and years. And we have we have different kinds of diodes, like power diodes and ideal diodes and the small power diodes and everything. So as far as industry is concerned, your diodes, the power diodes are more important. Like power diodes, usually these power diodes operate in a high voltage values compared to the normal diodes, and what we use in our laboratory for experiments are not high voltage. They usually operate in a very low voltages also. So but whatever it is, your PN junction diodes, the structure of the PN junction diodes is almost same, and for us this is concerned, let's see about the basic structure. So I'll start with this PN junction diodes basic structure. Before going to the basic structure, I'll just explain you what is a semiconductor. So semiconductor, as the name says, it conducts when excited by an external force or something, or supply or voltage of something. So usually you know what is a conductor. A conductor that conducts electricity whenever there is a voltage drop. So whenever there is a voltage drop, it conducts electricity. And an insulator which never conducts, does not conduct. So it does not conduct. So your semiconductor almost lies between this. It functions both as an insulator and a conductor. That is, this semiconductor is going to be a conductor only when there is an external force is applied or an external voltage is applied. That too, that voltage will be of some value, voltage of minimum value. So for example, if I have a wire that is connected to the battery, so this is a wire. If I put a diode here, so this is a symbol of the diode. So if I put a battery and connect a diode here, the current if there is no diode, without a diode, if there is a fully connected through a wire, the current can easily flow as when the voltage increases, when the voltage is formed. But when the diode is concerned, this diode will allow the current to conduct or allow the current to pass through only after a certain voltage range. That is, for example, these semiconductor devices, we use silicon and also germanium. germanium. In silicon, the voltage, the diode starts to conduct only when the voltage is increased about the 7.7 volt, and for germanium, it will start conduct only after 0.3 volt. This is for the normal diode. So by keeping the voltage below 0.7 or below this value, your diodes will never conduct. Only above a certain value of like 0.7 volt it starts to conduct. So this is a major thing. This is a semiconductor design. But how this semiconductor is constructed? So we'll see the structure of PN diodes. So usually what they do is we are going to study about the silicon semiconductor. So in silicon semiconductor, what happens is like they take a piece of silicon, I call it as a wafer, call as a wafer, you take a piece of silicon, but a pure silicon will not conduct because there are no extra electrons or free electrons to conduct. You know that conductor conducts because there is a free electrons present which can usually move due to some acceleration of the velocity created or the force created at both ends. But in silicon, purely if it is a silicon, it will not conduct. So what do you do is we add up impurities, we put some impurities into it. So impurity, if you put some impurity, this silicon becomes a semiconductor, so it can conduct at certain conditions. So this impurity is been classified into two types. One is the p-type impurity and another one is n-type impurity. So what does it mean from the word p-type and n-type? In p-type, we are adding an impurity which has the majority carriers, or the majority you have the positive or called as holes, positive charges which has the majority. And so when you add the impurities which has the positive charges more, then it becomes a p-type. And when you add an impurity which has electrons or negative charges as well as a majority carriers, then it becomes an n-type. So you can have a semiconductor device or semiconductor piece whether it is of n-type or p-type. So for a diode is concerned, this n-type and p-type is more important. It should be a combination of n-type and p-type. So as I told you, the adding of this impurity to the semiconductor device, that is to form a semiconductor, is called as doping. So this is an important technical word in the p-n junction diode, is called as a doping, which means that we are adding an impurity to a silicon. So when this doping is done, usually what we do is we can dope both the p-type and n-type separately for the two pieces of silicon. So for example, it will look like this, like I have taken a silicon of two pieces. The two pieces of silicon are equally doped, that is the doping level in the both will be the same. So it almost the size of that silicon will also is going to look like the same. So what I do is I'll keep the same copy of it. So this is going to be the same, it looks like the same. So the doping level is also big. So when I dope it here, it becomes a p-type. So you have the p-type semiconductors, like positive charges is going to be high compared to the negative charges. So we have the negative charges here. So as you see here, the negative charges are less compared to the positive charges, so that this becomes p-type. And for the n-type, what happens is the negative charges will be more. The negative charges will be more considered to the positive charges because we added a n-type negative impurities into it, so it becomes more. And when you say it is positive, will be less. So it means that the majority carriers here are the holes. So in this case, for the p-type, the majority carriers are mean like charges, carriers are holes, and for this is concerned, the majority carriers is electrons. So this is p-type and this is a n-type, right? So with this p-type and n-type, So as I told you, what happens is for forming a PN junction diode, they take this both p-type and n-type semiconductor devices and they actually start to diffuse it. So it's, the meaning of diffusing is joining. So what I do is I show it here. Okay, so this p-type and n-type, they start to diffuse it. So they are going to combine this n-type to this p-type, they're joining it. So literally it means joining, but the technical term is called as diffusing. So this is how they will diffuse. So it is called as diffusing, means joining. So once they do this, what actually happens is, you can see that here for this p-type you have an extra electron positive holes, extra holes are there. Like when you compare this number of holes and number of electrons in p-type, the positive charges are more, and for the n-type the electrons are more, the negative charges are more. So what happens actually when they are brought near the opposite charges, which are free electrons? These supposed to be the positive and the negative, supposed to be the free electrons, a kind of free electrons inside this n-type and p-type. So they start to attract each other and they just move towards the region close to each other. So they come to the junction. So this is called as the junction. The junction is formed due to the diffusing of the two layers. Okay, so they come close nearer. So when they come close near to this, they actually look like this. So I will redraw this because that will be much easy for you to understand. So you have the both combined structure of this p-type and n-type. So what happens is, these positive charges will try to come close to the board. So we can say like positive, 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 positive. So these are the positive charges which are moved almost close to this, and here also the positive charges will remain. Here only 3 columns of positive charges I'm showing you, and you have the negatives here. Okay, so what happens is, as I told you, when these combines, the positive, the extra holes and the extra electrons which is found near the junction forms a layer. They neutralize here. So as they neutralize, what happens is, it becomes a wall. So it becomes as a barrier here. Now they neutralize and they become diffused here. So it can be shown like this, like this becomes, this two combines and this becomes a diffusion layer. So this is called as a diffusion layer. So since it is formed due to the diffusion, it is called as a diffusion layer. Alright, so this is how it will start. Now this is how your PN junction diode looks like. It has two terminals, one at this end and another one is this end. So you know already this is a p-type and this is a n-type. So the p-type, the terminal near the p-type is called as an anode, which is denoted by A, and this K is cathode. So we can mention it. A stands for anode, which is usually positive, and K stands for cathode, which is usually negative. Right, so this is how your PN junction diode is formed. So next what happens is, this is how your whole process. So I'll repeat here. So you have semiconductors. In the semiconductor, silicon, we probably prefer for the silicon, not the germanium, because silicon has a high voltage, like the voltage level for the conduction is 0.7 when compared to the germanium, which is 0.3. So usually you see the silicon semiconductors are mostly in your market, and then what they do is, this pure silicon will not conduct, so they add impurity to it. So the adding impurity is called as doping. So doping is a process of adding the impurity to the semiconductor. So the doping can be done, the impurity can be either positive impurities or negative impurities. It's called as p-type and n-type. So when you add this impurity, what happens is, silicon semiconductors, this silicon semiconductor will become either p-type or n-type depending upon the doping. And it is one more clear that the doping level of both p-type and n-type should be same. So that is very, very important. The doping level should be same, only then it will be work finely. Okay, so you can note this point as that the doping of p type should be equal to doping of n type. That should be always noted. And what happens is in the p type and n type, you have the majority carriers for the p types as holes, which is positive, and the majority carriers for the n type will be the electrons. So on this basis, in the construction, what they do is they start to diffuse. Diffuse is joining the two layers of like p type and n type. They're joining it, forming a junction. So when they join, they form a junction. And since the p type has extra holes and the n type has an extra electrons, which is a free electrons, so in that case it is a free holes, they start to attract each other and they come closer to the junction. And once they come closer to the junction, due to the diffusion, and they start to neutralize, that is the positive and negative charge changes and they become neutralizers, and this forms a diffusion layer. So this diffusion layer is going to be act as a barrier, diffusion layer, or it is also called as a barrier layer. So barrier is nothing but it is not going to now allow, it is not going to allow any flow of current into it. Now this device or semiconductor is not going to conduct until the diffusion layer is made. So in operation of this, in operation of the PN diodes, we are going to see how this electron, that is how this conduction is going to take by breaking the diffusion layer, because it is already understood from the visualization that since the diffusion layer is present, there is the movement of holes or the electrons from one layer to another is not possible, because it stands like a wall. It's almost like a wall which is going to which is separating these two layers. So now we have to provide an external voltage or external force that is going to break this wall and all the diffusion layer, and then it's going to conduct. So in this operation we are going to see two types of operation. One is the forward bias, and the next one is the reverse bias. Okay, in the electronics we call as bias means conduction. So the word bias is already, should we be familiar with the word bias refers to conduction. So if we see how the forward bias is conducted, so already you know that there are two terminals, anode and cathode. Usually anode keeps in always in positive, and cathode is found in the negative layer, that is the n type layer of the semiconductor. So what happens in the biasing of a forward biasing, let me show you. We have a semiconductor device which is now diffused. So the diffusion layer, I will draw it here, and this is going to be the p type, and this is going to the n type. Now for the forward, I'm going to provide an external force or an external voltage to this device to let me see how it's going to work. So I take a battery, and I have the positive side of the battery connecting to the anode of the p type, that is anode of the semiconductor, and the negative terminal of the battery will be connected to the n type of this. Okay, so this is the positive side of the battery and this is the negative is also. I will keep the battery voltage as input voltage, which is VIN, and this VIN can be varied from, let me take from 0 to 30 volt. Okay, now initially it is in 0. Okay, so we know that your I'm going with that your p type is already have this is more of like, you know, it's a positively charged, it is more of positively charged, and the n type is more of negatively charged. Okay, more of negatively charged, this is, you know, that. Okay, so what happens is when you put on your battery positive to the anode, so I'll take this as an mark it as anode A, and this is cathode. So initially at the point of 0, that is, I'll show you by graphically so that you can understand easily. I'm talking x-axis and the y-axis. In the x-axis I'm talking the input voltage, and in the y-axis I'm going to take the current, that is the current flowing through the PN diode, current I. Alright, so initially at the point of 0, there is no conduction. So as I change my value from up to, I told you for a silicon the voltage at which it starts to conduct is 0.7 volt, right? 0.7 volt. So let me see up to what happens in the 0.7 volt. So what I'm going to do is I'm going to increase my voltage from 0 slowly, like 0.1, 0.2, 0.3 and up to 0.1 until it reaches 0.7. there will not be any conduction, so there will be only small leakage current flowing through it. And to you also to remember this, when the p-type layer is connected to the positive of the battery, you are already, it means that you are supplying the more, you are making the p-type more and more positive. What is that? You are going to make more and more positive. And initially before starting this voltage, giving up the voltage, the positive and the negative in the p-type will be, the count will be number same, and similarly in the n-type region the negative number of electrons and number of holes is going to be the same. They are like, it's kind of a neutral, they are not going to do it. There is no free electrons, because these free electrons have already been diffused in this layer. Okay, so now what I'm going to do is, since I have connected the positive to the battery to the p-type, there more and more positive charges are going to be accumulated in this region. And since the negative terminal of the battery is connected to the n-type, more and more it becomes more and more electrically, that is again negatively charged. This is going to be more and more. So you are this layer, there is both p layer and the n layer are both are going to gain holes and electrons respectively. They are getting more and more free holes and free electrons here. So what happens usually, as you saw, when there is a free electrons or free holes, they start to attract each other. So now what happens is, they again start to attract this positive, extra positive charges and the extra negative charges in the p-type are going to again attract to each other. They will be pushing, or they will be coming closer again and again. So what happens, this holes and the holes and electrons will try to break this barrier, because they are getting attracted. That it means the force at this layer, at this point, the force are trying to now push the positive charges towards this and trying to push the electrons towards this side, electrons to move from the other side, and the positive holes to be the other side. So what happens, due to the force created, the barrier breaks. And since the barrier breaks, now it gets a channel. Actually the barrier does not break immediately. It diminishes and keeps on, and at a time when it breaks, the current starts to conduct. So now the current can start to move here. So the conduction starts. So it happens actually at the point of 0.7. Until 0.7, the diffusion layer will start diminishing, and at the 0.7 the barrier or the diffusion layer completely breaks and it starts to increase. The conduction starts, and this point at which the current starts to conduct is called as the threshold voltage. Threshold voltage we call as a VT. So we know the threshold voltage is nothing but the minimum voltage. We call it as a minimum voltage above which the diode starts to conduct. Right? So this is how your forward bias looks like. So for the forward bias, the mandatory, like, your anode should be connected to the positive of the battery and the cathode should be connected to the negative of the battery. So as I told you, since it is getting more and more positive in the p-type and getting more and more negative in the n-type, there is a force of attraction which overcomes the diffusion layer or the barrier, and they break it and they go on. So usually the start of the condition will be like your input voltage, when it's greater than VT, it starts to conduction starts. So below, if Vin is less than VT, there is, or up to less than or equal to VT, there is no conduction. Right? So this is the important point in the forward bias condition. So now let's see what is the reverse bias condition. Now in reverse bias, by the name itself you can feel that the conduction is going to be reversed. That is, you are going to change the battery terminals. That is, you are going to connect in the opposite direction. So let me keep my p-type semiconductor, p-type or p-junction diodes in like this. So I have an anode and this is anode, this is the p-type and this is n-type. Now what I'm going to do is I'm going to reverse my terminals. So I reverse my battery so that I connect my anode to the negative of the battery and the cathode is connected to the negative positive of the battery. So this is my cathode and this is the anode, so it is connected. So the negative you have now reverse yes, so this is a V. So here also I'm going to apply a negative voltage. I'm going to increase the negative voltage to this. So since because it is connected in the opposite direction, I mean to say it is a negative voltage because the current direction is going to reverse. That's the meaning here. So already you know your there are the positives are more in the p-type, which is already I've told you, and similarly the electrons are more in this region. Okay, so equal amount, so it means, and there is a barrier in between these two due to the formation of diffusion layers. Okay, this is how it is. Now what happens when I start to give my negative voltage? So what I'm going to do is, like, I'm going to show you a graph where I'm going to apply a negative voltage. So the current here is going to be also negative because of the opposite direction. So I will draw it in the third quadrant. I'm showing you the third quadrant region here so that it will be easy for you to understand. So it is minus V in and this is the minus I current, which is a reverse current. So what happens exactly? So at the point of increasement of this voltage, when the voltage is increased from the voltage from 0 to increasing the value, but in the since it is a negative direction, I'll keep talking about the positive value of the voltage. You should understand, since it is connected in the opposite reverse direction, it means to be a minus voltage. So as I increase it, what happens is this electrons, this negative part of this, which is connected to the anode, it makes this p-type gaining some electrons into it. So electrons get accumulated, it becomes still gains electrons here, and similarly here it gains positive charges electrons. So what happens, these positive charges in the p-type, is now getting attracted towards this the newly accumulated negative charges, and these holes starts to move and get attracted to the outside of this part. They are moving up away from the junction. These positive charges are moving away from the junction, and similarly these electrons are going to move away from the junction and reaching the terminal point because they have an opposite charges accumulated at this point of cathode. So what happens, there is instead of diminishing, they are going to expand. Now the diffusion layer is now going to expand. Due to this, the diffusion layer will expand irrespective of this previously manufactured. So the diffusion layer is increasing. So ultimately, if the diffusion layer is increasing, what will happen? There will be no conduction. So what happens, from the point of 0, as you start, the voltage increases, it will have a very, 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 very small value of current until at a point of something where the voltage is negatively increased a very greater value, immediately the breakdown occurs and the current starts to fall down. There's a increase in the negative side to a higher, keeping the voltage constant. And so this point is now called as the breakdown voltage. It's called as a breakdown voltage. Usually happens in the reverse bias. And in this, absolutely, since because it is in the breakdown, we don't say that there is a conduction. There is no conduction. And this region where we saw here, this is going to be the negative leakage current, which will be in terms of microamperes. It will be in terms of microamperes, which is not being used practically. It cannot be used, and theoretically, as I say, there is no conduction. Theoretically, I mean to say conduction. And similarly, the current in this forward bias, which is before the 0.7 voltage, will be in the terms of milliamperes. Even this is also called as a leakage current. Right. So this is how your forward and the reverse bias actually work. Right, so this is a breakdown. For breakdown, you can say the minimum voltage above which the current increases in the negative, keeping the voltage constant or we can also say it is the device breaks. Device will break. So this is how your conduction, that is the forward and the reverse bias, actually takes place. So combining this forward and the reverse bias, we can easily now state for the VI characteristics. So VI characteristics. So in the VI characteristics, I'm going to draw the graph. I'm going to have the voltage in the x-axis. So I'll mean to say for the in the right side of the plane, I'm going to have the forward voltage Vf, and this is supposed to be the reverse voltage, and this is the forward current If, which will be in milliampere, and this is the reverse current Ir, which will be in the microamperes. Okay. So for this, now as I told you, in the forward bias, when it initially at the point of 0, the current remains here, and it will have some leakage until it reaches 0.7, and when it reaches 0.7, the current starts to increase. So this point is called as a Vt, which is nothing but a threshold voltage, and this is where the conduction, so forward conduction takes place. So this is a forward conduction taking place. And for this reverse is concerned, for the reverse value is concerned, so there will be very small, I'll draw it in this color, it will be very small compared to, and suddenly it falls steeply, forming a knee, and this point is called as a breakdown voltage. What is a reverse conduction, or is a reverse conduction? But theoretically, as I say, there is no conduction. Actually, we don't say it's a reverse conduction. Reverse biasing region, reverse bias region. I'll better put it as reverse biasing region. So this is how, this is actually your VI characteristics of an PN junction diode. So when you, so it is understood that for any conduction, your diode, so let me also tell you how the diode symbol look like. So it will have a diode symbol like this. You will draw like this, and the straight line which has this near, which is called as a cathode terminal, and this is the anode terminal. So always remembered that the current always travels from anode to cathode. Only when the anode is kept positive and the cathode is kept negative, the current will start to conduct. So this is how it will look like. So this current will conduct only when your input voltage or the voltage drop across your diode is going to be greater than the threshold voltage. That is, in case of silicon, it is going to be 0.7 voltage. Right. So this is your VI characteristics of the PN junction diode. So this is a very important thing, when very basic before understanding the other semiconductor devices. This is how the basics of other semiconductor takes place. So you should remember the structure of the PN junction diodes, and for the P type and N type impurities, as I told you, there are different materials which come under the come under the P type and N type. You can search it on Google it, and we can find what are the type of impurities that makes it P type, and what are the other type of impurities which makes an N type, that you can Google it, and you have to join this, or that is a diffusion forms a layer and something. So the diffusion layer is formed. So to break the diffusion layer, to make the conduction, you need to make a forward bias operation, and the reverse bias is usually not done practically because it doesn't going to conduct anywhere. Okay, so this is how to remember. So as far as this PN junction is diode is considered, there are some points here to remember. That is, your PN junction diode is a two-layer device, which is nothing, one is a P type and the N type layers, and since the two layers is going to form a one junction. So one junction is a two-layer and one junction device, and it conducts only in one direction. So it conducts in a unidirectional. Unidirection means only one direction. So you can say PN junction diode is a unidirectional device. It conducts in only one direction, and rest of the things of what I told you is like this. So for conduction, only forward bias is allowed. Forward bias is used for conduction. So this is your PN junction diode. So in the next class we will see about that how this diffusion capacitance and transition capacitance are actual working of this PN junction diode, how these equations are formed, the derivations you will see in the next class. So thank you for joining.